Okay, everybody. So this is the video for week 11. And what we're going to be doing is we're going to take a look at the introduction to numerical differentiation here in the lecture one notes. And then also we might take a peek at the lab for this week in case anybody misses the lab and needs a little help getting started with it. Um, so we'll open both of those pages. I'll open the lab and I'll open the introduction here to numerical integration. And we'll just head over to the page. That did not load correctly. There we go. Um, so this is actually a pretty simple topic. What we were doing in the previous weeks, where we were trying to solve differential equations, is quite a bit more complicated than what we're doing this week. Um, that's just the way kind of the book went because we had sections on numerical solutions to differential equations, but we didn't really have these kind of finite difference formulas like we're looking at today. Which, by the way, like finite difference formula, that's kind of a vocab word. You'll hear that if you're taking like more engineering classes going forward. Um, so yeah, all right. So what's the point? So as it says up here, in many scientific and engineering applications, we need to find the derivative of a function. But sometimes, we've got a computer and we don't have a way to take the derivative of the function because maybe the derivative doesn't, we don't know what the analytic solution the derivative is. Or, I mean, maybe, it's just a complicated function and we don't feel like taking a derivative by hand, right? So for whatever reason, we're going to be doing this numerically, right? So it says like this occurs when the function is defined by a set of discrete data points, like sensor readings. Yeah, that's also a big deal, right? Like if you collect a bunch of data that represents your function, then you don't know what the function is as a formula. So you can't possibly take the derivative of that, right? If you don't have it written out, you can't take a derivative. But if you have data, we can still crunch the numbers, okay? Um, so numerical differentiation, right, is going to use discrete values of the function to estimate its rate of change. And that's not hard, right? Because I guess it's not listed here, which I should fix that. But the formula for a derivative. Let's just we'll Google here. What do we want? We want, let's see, derivative formula. This is all because I can't, um, here we go. I'm sure the first link will have it, right? No. Yeah, no. Oh, come on. Give me the cheat sheet. There we go. Symbolab cheat sheet. No, that's the rules. I want the formula, the limit-based formula. That's all I'm looking for. Limit. Aha, there we go. This is all I was looking for. Um, so of course, when you first learn about derivatives in Calculus 1, this is the formula you're looking at, right? That f prime at a particular point, so this is an a value that we know, and it's the limit as h goes to 0 of this thing. And so you take a limit as h goes to 0, and that's going to be your derivative. But if you think about that, this thing right here, f of a plus h minus f of a over h, if you've only got specific numbers, you could not possibly calculate this, right? You can't do a limit. But what you can do is you can put in a value for a and you can put in a value for h. And if you put a small h, then this should be approximately equal to the derivative, right? Because if you remember where this formula comes from is it's the slope of a secant line. And as h gets smaller, the 2 points on the curve get closer and closer together until they're overlapping, right? Like if I go to Desmos, I don't know if this is going to be a good idea or not. Um, I don't know how to do this. I don't think I can. Maybe, what if I do f of x equals that? Is it possible to say 2 comma f of 2? Haha, it is. Um, cool. So like you have a point there, right? And I could pick like another point and just say like a comma f of a. We can have a slider. And so what's happening here is that if you have 2 points on here, they could be separated by h on the x-axis, but then they're separated on the y-axis too, right? But as this point gets closer, right, you could have this point get closer and closer and closer to the other point until they're essentially overlapping. And that's what you do when you're taking a limit as h goes to zero. But if you can't take a limit as h goes to zero, you can just pick a small value of h, and then this function value and this function value will be close together. And that's great. So what you'll see here is limit h goes to zero, f of a plus h minus f of a over h. And if you look at the notes, what you'll see in this formula for our first estimate for a derivative is it's just f of x plus h minus f of x over h. The only difference is there's no limit. Also, they have x instead of a, but there's no limit. So we're just choosing a small number for h instead of taking a limit as h approaches zero. And so this is what they call a forward difference. And in lecture, right, I'm going to talk about this and I'm going to draw pictures and stuff, but I don't have a picture right here. So what does this mean? Well, like if I head over to Octave to where I could type a little bit, we'll just make a little script. So let me make a function. So we'll make a little function. So we'll say like f equals, and we'll try f of x. And what will it be? I don't know. Let's do x cubed. Um, so I'll save that. I'll call this something. What do we call it? Derivative dot m. So right now, if I run this, okay, it runs good. And if I were to just pick an h value, like h equals 0.1, and I pick an a value, so like let's say a equals um, 2, we'll put semicolons there. And then I calculate this, I'll say like fp for f prime. And if I do f of a plus h minus f of a divided by h, whoa, divided by h, then that should be approximately equal to the derivative. So if I save this and I print it out, we get 12.6 here, right? Now, we know that the actual derivative of this function, right? So like the real derivative, so I'll say real fp, right? The actual derivative of this function is 3 times x squared, right? Because the derivative of x cubed is 3x squared. We've all taken calculus, so we can do that. So fp is this, but I don't really like how I did this. Let me just kind of redo this. fp, we'll call that f and fp. And then here, instead of calling this fp, this one we'll call like fp, fpa prox. And then we'll have fpa real. And the real fp is we would just have to put into fp, we'll put in the a. So let's just save that and let's run it and see what happens. So we can see that the approximate derivative is 12.6 using my little formula. And then the real derivative, of course, is 12. So that's just take the derivative of x cubed to get 3x squared, and then you plug in a 2. We get 12. Now, changing the h value is going to change how good of our approximation is. So if I change the h value to 0.1, the error should get smaller. In fact, actually, let's do this. So error is, you could calculate the error just by taking the real value. We'll just do the absolute value of this, of the error. So we can do the real value minus the approximation. And that's the absolute value of the error. So how big the error is. So let's save this and do that. I've got an extra set of parentheses, so let's try it again. All right. So of course it just says what we know, right? Like the if the real thing's 12 and the approximation is 12.6, then our error is about zero point 0.6. But if I change this h value to 0.1 and we save it, now it's 0.06. So good. If I change it to 0.001, now it's 6 times 10 to the negative 3, which is 0.006. So basically, every time I add a zero here, I'm getting an extra zero in the error. So as the h gets smaller, the error is going to go smaller as well. So, okay. There's other things we could do here too. Like we could just keep making this smaller, but in order to make it smaller, maybe we should write this in kind of a different way. Like maybe we should do 1e, that's engineering notation. So this is 1 times 10 to the, right? And if I go 10 to the 2, that's like an h value of 10 to the negative 2. And that's what we just were. If we change that to a 3, I don't think saving works. I have to hit save. 6 times 10 to the negative 3. If I change it to a 4, we get 4. I'm going to jump to I'm going to jump by twos now. I'm going to go 6, and it's 6 times 10 to the negative 6. If I go 1 times 10 to the negative 8, I get this. Notice that this is starting to change. If I go 10, oh, actually the error is now higher. Now the error is now higher. Um, and so basically, smaller h value works up until a certain point to make the error go down. But then at a certain point, I guess around this 10 to the negative 8 value, the error actually starts going up. If we wanted to see that, we could try to make a plot of this, maybe. So how about instead of doing this, our h values could be, maybe we'll do this. Um, 10 to the power, then we'll do -1. Actually, we'll do -2, -4, -6. Well, I don't like that. We'll do, I don't know what I want. Um, -1, -1, -12. Will this work? Um, then I'm going to comment this out for the moment. We'll save this, hit run. Okay, it's running okay. I just wanted to make sure. And then kind of, we're going to take this work here and we're going to wrap it in like a for loop so I can find the error for each of these, each h value. So we'll go from for I equals 0 to the length of the h vector. Um, and there I decide I actually want to call that hs and not h. And then in here, what I'll do is I will uh, get an h value from my h's. Okay. After I do that, I will calculate this approximation. I will calculate the real value. We don't really need to calculate the real value every time, but I'll do it anyway. And then I kind of want to save the error somewhere. So let's calculate the error like this, but maybe we'll do error I, and we'll calculate the error. And then I can end this like so. And in theory, we'll have when we're done. In fact, let's run this and see. what we'll have when we're done is uh-oh, HS0. Okay, this did not work. Um, V -1, -1, -12. I don't know if this is gonna work. Let me see. I I didn't read that error very carefully. Let's see. Okay, same thing. HS0 subscripts. Oh, yeah, sorry. This is just me forgetting what programming language we're doing. We can back this up. Uh, sorry, that's my mistake. Indexing in MATLAB starts at 1. So I tried to start at 0, like we would in Java or C++. Okay, let's try this again. Right. Okay, so that runs. We probably could have semicolons there. All right. So at this point, we've got like the errors here in this little table. So as the h's get smaller and smaller, right? The h's are like 10 to the -1, 10 to the -2, etc. The error goes 6 to the -1, 6 to the -2, 6 to the -3. Actually, that's not the error. That's the what is that? What is appearing on our screen? Oh, okay. This is from the previous problem. Um, Yeah. Okay, so these are the errors. I lied to you. So 6 to the -1, 6 to the -2, etc. And that goes down to like 6 to the -6, and then 5 to the -7, um, and then 7 to the -8. Like the pattern is kind of falling apart here. 10 to the -7, 10 to the -7, 10 to the -7, and then 1 times 10 to the -3. So that's like bad. So the error went down to about 10 to the -8, but then it comes up a little bit. And so at some point, the error just stops getting better as we decrease the h size, even though technically, from a theoretical standpoint, the smaller the h value, the better the result should be. And let's try to plot this result. So if I try to plot the h values and the error values, we should be able to do that. I'll plot it with, let's just say, like red circles. And let's also do, I think, marker size, and let's make it 10. And so let's just try to look at our errors. Um, I don't really see them. So I see that I don't really see what's going on here in our plot. That doesn't look good. Maybe let's try this. Oh, oh, okay. So you see the problem here is that all the circles are kind of together. Oh, they're together because I plotted H when I should have plotted HS. Okay. Okay, there we go. And so what this is showing is that like this plot's not very good. So the first H value is 0.1 or 0.01, which is here. No, the first one's up here, zero point 0.1, then 0.01, then 0.001. And the errors are also very close to zero. So because the H values are going to zero and also the error is kind of small, you just get a whole bunch of circles overlapping down here. And so this is not really a good plot in order to look at this. And so they like to use, instead of a regular plot, they like to use a what they call a log-log plot. So if I replace this plot with log and we save it, so I just changed the word plot to log-log and we plot this, what you'll see, and this is a lot nicer, is that you'll see that instead, like on the y-axis, we have like 10 to the 0, 10 to the -1, 10 to the -2. So we have like powers of 10 on the y-axis, but we also have powers of 10 on the x-axis. And so that allows us to see our values better because they're not just all bunched up at 0 now, right? Because if you think about it, like 10 to the -12, 10 to the -11, 10 to the -10th, 10 to the -9th, etc., right? These are all basically 0. And so we had a whole bunch of overlapping circles when we had the other kind of plot. Now, to try to make this plot a little more visible, I can go back and add the stuff that I was trying to add before. So like we can try to add marker size, um, maybe 10. We can try to add line width and try to make that like 2. And we could add X label, and the X label were the H values. And we could do a Y label, and the Y was the absolute value technically of the error is what we plotted. Um, and then give it a title, plot of error versus H. And then we could put a grid on it, and then maybe we'll save it. So we'll do print dash D PNG, and we'll just call this you know, H error plot dot PNG. All right, so let's save that. Let's run it. Hopefully our plot will be a little more nicer looking. Sort of. It's sort of nicer looking. But I think we can see it okay, actually. So what we should be able to see here is our H values are like this is 10 to the negative 1, right? 0 0.1, 0 0.2, 0 0.3, 0 0.4, or sorry, I mean 0 0.1, 0 0.01, 0.0001, 0.0001, 0.00001, etc., right? Like we're going closer to 0 this way. And so what happens at first is as the H value gets smaller, the error goes down and down and down. And then around here, 10 to the negative 8th, that's about as low as the error is going to be. And then if you try to pick lower H values, then the error is kind of higher. So these are all the same. And then this last one somehow is way higher. And that's typical. And because from a theoretical standpoint, lower H is better. So that's why it goes down and down and down. But at some point, the computer's precision is an issue. We only have about 16 decimals of accuracy. And because of that, when numbers are small and you subtract one small number from another small number, um, like you could have, how should I put this? If you have 16 significant figures for two numbers and they're really close together, maybe they only differ in the last like 2 digits. Then when you subtract them, you go from having 16 digits, significant digits, to having two significant digits, which means you now have a lot of error because you only got two significant digits versus 16. And so at some point, that's what happens. And the computer doesn't have enough precision to actually come up with a better answer than this answer right here. So if you try to go below this, you'll end up with higher error. And I wanted to make that point. And but other than that, this is, we were calculating derivatives. Now, once we can calculate a derivative, the next thing we want to do is see if we can write a function that does this, what we called over here, um, the forward difference. And now this is a really easy function to write. Okay, so if we come over here and I just have one already written, let's just delete the code. Um, so if we wanted to try to calculate a forward difference, you could just say like, well, what do we need? Well, in order to calculate this, we need an F, an X, and an H, right? And so we need an F, an X, and an H. So those are inputs to our function. The output is the derivative, which we're calling dy here. And then how would you calculate this? Well, dy is, so dy is a derivative, f of x plus h minus f of x, f of x plus h minus f of x, and then all of that, so parentheses, over h. Now, what you should do when you're coding this up, though, is you should put a dot here because that will allow us to use multiple x values at once, and that will be useful. So we'll put dot slash there, and we'll save this. And now that we've done that, that's really nice because, like, for example, here I have this f, and if I go up to the command window and I say like f of 2, right, we can get a value. But we can also use forward diff now, forward diff, and we can give it an f, an x, so we were using 2, and an h, like 0.1, and what is it complaining? Parse error? Oh, dot slash, not slash dot. Try again. So you see, we can put this difference formula for estimating the derivative in a function, and then I can just give it the f, the value, and the h value I want to use, and I can calculate it. So I could do um, like whatever h values I want, and you can see that as I do this, this is getting closer and closer to 12, which of course we remember was the real value. So the smaller the h value you use, the better this gets. And going back to my script, which I think I just called derivative, you can now, this approximation here, you can get rid of, and you could just say forward diff f a h. And then we don't have to calculate it in the middle of the script. So this should be the same plot we've already seen. Okay, so what did we do? We just estimated a derivative using this forward difference. Now, what we would like to do though sometimes is to make a plot of something. So if let's make a new script here, and I'm going to call this like plot the derivative. So let's define a function. So let's say f equals at x, and let's just do sine 2 times x. So that's a very simple function, right? And let's plot it. So let's do plot. Oh, we need x values and stuff. So let's do x is going to be, let's say 0 colon 2 times pi, actually 0.01 colon 2 times pi. Okay, and that's fine. And then we can do our f of x values, or our y values will be f of x. And then if I plot x comma y, we should get a nice plot. So let's say derivative plot dot m. Okay, so what is this? So this is our sine function over 2 pi. So we have like 2 periods, it looks like, and it goes from 0, maximum of 1. Of course, it's a sine function, so it goes through 0, 0. Everything's fine there. Um, Now, what if I want to plot the derivative, right? Well, we can calculate the derivative now with our function that calculates derivatives. So let's do file save. So the way that we wrote this forward difference is that we should be able to plug an entire x vector in there. So we should be able to pick an h value, whatever h value we want, and we should just be able to say like fp for f prime. What is it? Well, we should be able to do it with a forward difference, and we give it an f. We give it the x values, which we can give it our entire vector, and we give it an h value, which is whatever we want. So I can do like 0.01, for example. Save this, and I guess I want to plot it. So we would be the x values. I should have called this, maybe this should be y prime. So x comma y prime, and let's also give that a line width of 2. Let's give it a grid. Let's give it a legend of y equals sine 2x. And the other function is the y prime, right? But what's y prime? I think y prime would be 2 cosine, right? 2 cosine 2x. Would that be right? Also, notice that you might notice I typed 2 apostrophes there. That's intentional because I think the legend will require that and it'll actually say 1 prime there. All right, so what do we have? So hopefully this should look like the function and its derivative plotted in a single plot. Okay, so what did we do? We made a plot. We have a function called forward difference that calculates a forward difference. We've got a couple of scripts to do some calculations. We saw that the H value goes down. As the H value goes down, the error goes down to a point, but then it increases again. And we made a plot of a derivative. So that's mostly what we wanted to talk about. But we can go over more of this in class. But what we're going to do is we or you are going to test these other functions out. So we did the forward difference, but in the homework, you'll do the backward difference, or I should say the lab, not the homework. And you're going to do this called the central difference. And all of these are approximations for the derivative, but you'll see that the central difference works out a little better. And also you'll see here that the H value of around 10 to the negative 8 is generally better. But you are going to investigate this yourself, okay? So in the lab, whoa, that also loaded incorrectly. So in the lab, you're going to try out the backward difference, or actually you're going to code up the backward difference, which is like almost identical to the forward difference. Um, I'm not 100% sure this derivative is correct. We'll check that in class today before we try it out. But we're going to try to um, estimate the derivative of this function, which I made complicated on purpose, over this interval. So that's like what we were just doing with the plot. Um, you're going to use h equals 0.01, which is fine. And then you're going to try to calculate the maximum error that you get over that range. And that's going to be similar to a plot of some code, or that's going to be similar to some code that's in the notes that we're going to look at. Then you're going to do the same thing with the central difference, which means you can basically reuse your script from problem 1 for problem 2. But you'll have to write this central difference uh, function. Not that it's hard, it's also a one-line problem. You're going to see if that generates better results. You're using the same H value of 0.01, so you can see if you get a better error or a worse error. We're going to try out different step sizes. I would recommend you look at what we just did in order to do that, since we just did something similar to this in earlier in this video. You're going to basically do the same thing for forward, backward, and central differences, where you check out what H value gives you the best result for each of the methods. And then finally, you're going to just mention, what we discovered here. So like which method was the best out of the 3 that we tried, which H value is the best for forward or backward or central, and that's about it. So that's the lab for this week. I think this makes some amount of sense. And we'll stop the video here and I'll talk to you guys later.